Hello guys, today I want to talk about green theorem. First of all, recall that with line integral, we can integrate along a curve C, and if we have a vector field f equal pq, then the form of the integral is the C of f dot dr, which become the integral along C of p dq p dx plus q dy. This is the case for all curve C. Now we go to the next slide. However, a special theorem exists for closed curve, that is curve that form a complete loop and enclose an area which we will label D. This is D. For this case, the line integral over C of p dx plus q dy end up being equal to the double integral over the domain D of dq over dx minus dp over dy dx dy. This is called Green theorem. This is a very useful theorem, as line integral are typical hard or more complicated to calculate than ordinary integral. Okay, next. Before we move to question, there an important distinction we must make regarding the direction of the curve. Green theorem apply to closed curve that run counterclockwise. This is a curve that run counterclockwise. Another way to think of it, it's if you walk along the path in the direction of the arrow, the enclosed will always be on your left. This is referred to as a positive orientation. This is for this curve positive orientation. For curves that go in a clockwise direction or negative orientation, this is negative orientation, Green theorem can still be applied, but with a sign change. So the line integral can still be expressed as a double integral, just with a negative sign. Here you can see. It will be important to remember this detail to get a correct answer. Okay, that's all from me. Thank you.
So for today, I would like to show or evaluate the graph into software. So firstly, we must draw the first equation graph, which is C is equal to X with the power of 2 plus Y with the power of 2 equals to 1. So we can see the graph is like this. Okay, so this is the circle graph. Okay, for the next, we must show the graph in C is the ellipse, which X is the power of 2 plus Y with the power of 2 divided by 4 equals to 1. So we can see the graph is in the ellipse. So the purple one, this is the graph for the ellipse. So lastly, for the conclusion for the graph is C with X power of 2 plus Y with power of 2 equal to 1 is clockwise. Okay, we can see the arrow is right this. So this equation, the graph is shown like this. It is in the circle. But for the next equation, X with the power of 2 plus Y with the power of 2 over 4 equals 1 is anti-clockwise. Anti-clockwise is this. For this equation, this is represent for the ellipse 1, which is this is anti-clockwise. So this is all the graph. So from the graph we can make the other calculation. Okay, thank you.
I will explain about our question is that is consider the integral that is expression that are given. The question is evaluate it when c is the circle x square plus y square is equal to 1. Okay, here is the solution. From the equation that are given, we can come up with this equation P and Q. P that is equal to negative y over x square plus y square. Q is equal to x over x square plus y square. And so P and Q are not differentiable at 0, 0. Uh, so not differentiate everywhere inside the region enclosed by C. So we can't apply Green's theorem directly to the C and then this enclosed by it. Whenever you apply Green's theorem, remember to check that P and Q are differentiable wherever inside the region. But away from 0, 0, P and Q are differentiable and you can check that by this equation. However, because of the x square plus y square terms floating around in the integral, it is not too hard to compute the line integral over circle directly. Parameterize c as cos t sin t where 0 is smaller than t is smaller than 2 pi. So from this information, we can come out the solution this. So from this answer, we can get the graph likely just like my friend Fahim just explained. That is, we have a skull shape, skull. I mean skull. Okay, that's all from me. Thank you.
Hello everybody. Now I will continue to answer the example 1 of the green theorem. Question B. The they already given the equation, the integral that already shown in my slide. The question B will gonna be sound like this. C is the ellipse of x square plus y square over 4 is equal to 1. So we will evaluate the integral by the question B that already shown. All of you will notice that the ellipse x square plus y square over 4 is equal to 1 lies outside the circle of the radius 1, which we look at in part A that already answered by my friend Hairul Amri. In between the two curves bound some region D. Notice that on D, our P and Q are differentiable. The only problem point was the origin, which D avoid. So we can apply Green theorem to the region D with a hole with a boundary of C prime. The boundary of C prime, that all of you will notice that the boundary will gonna be like this that already shown in my slide. The C prime pdx plus qdy, and uh, we will continue until we will equal to 0, where the integrated becomes 0 because of the equation 1 whole. Now C prime is the compound of the two curve C1, the curve C1, the outside curve, our ellipse on the outside going counterclockwise. We will saw the arrow is will go to counterclockwise, and C2, the circle in the inside going clockwise. we will saw the arrow of C2 we will go the counter clockwise, and we will saw the region D. So by the uh, curve that already shown, we will get the equation, the integral of equation will stated like this. The integral of p dx plus q dy we will equal to integral c1 p dx plus q dy plus integral of c2 p dx plus q dy. But we just saw the equation 2 that uh, but the integral of but oh sorry, but the integral over the c2 is just the integral we calculated in part A, but with a negative sign c2 goes clockwise instead of counterclockwise. So the integral of p dx plus q dy will gonna be the c integral of c1 p dx plus q dy minus 2 pi. Now we will solve the equation 2 that the integral of c prime p dx plus q dy will be 0. So because of that, we will get the integral of c1 plus p dx integral of c1 p dx plus q dy will be 2 pi, which is exactly the integral over the ellipse that we wanted. All of you have to note that this argument actually show that in this example, the line integral over any closed curve about the origin will be 2 pi. That's all from me. Thank you.